Hello everybody, welcome to the Engineering Geology webinar channel. In this channel, latest geological and geotechnical insights applicable to various projects such as mining engineering projects, civil engineering projects, water and irrigation development projects will be discussed. So these are mining projects, failed slopes, and these are also landslides and at mining sites, and these are also mining sites. These are road projects, rockfall are road projects. These are also slides and falls at road projects. These are stable bench face slope angles on mining sites. My name is Dr. Birhanu Ermias, and I am an assistant professor of engineering geology and freelancer as geological and geotechnical expert. Today I am going to introduce you with the rapid stability assessment method of excavated rock slopes in the field. This concept will be covered with discussions recorded in a series of episodes, and each episode will be uploaded in once in a week. The overall content of stability of excavated rock slopes in the field is divided into 5 parts. In the first part, is about introduction to stability of excavated rock slopes in the field. The second part, the best method for rapid stability assessment of excavated rock slopes in the field will be discussed. The third part, application of the best method with case studies will be discussed. And the fourth part, the support system suggestion for slopes based on the best method will be discussed. Finally, in the final fifth part, we will discuss about advantages of the best method over other empirically derived slope stability assessment methods. So when we come to the first part, that is introduction to stability of excavated rock slopes in the field, the relevant question we need to ask is why rapid assessment is required for stability assessment of excavated rock slopes. So the answer for this question is because it is practically impossible to assess the stability of rock slope cuttings and the benches in real time using analytics such as kinematics, limit equilibrium, finite element methods, discrete element methods, or finite discrete element methods, because these methods, these analytical methods takes time, requires also input, and also these methods are methods or analysis techniques that we carry out in office, not in the field. Okay, rapid assessment method is required for stability assessment of excavated slopes in the field, while these methods are the methods that we apply them in office and requires some softwares and inputs. So it takes time to conduct this analysis and produce results that will be utilized to conduct the excavation. However, while the excavation is undergoing, it is not possible to apply these techniques, because these techniques are office work techniques, not field work techniques. The field engineer cannot apply these techniques while excavation is undergoing. So excavation is usually too fast for roads, benches, railways, open mines, tunnels, bridges, and dam sites. It's too fast, and what is required is the method that enable a site engineer or engineering geologist to go along with the excavation, evaluating the slopes and giving recommendations. So a method that allows engineering geologists and rock engineers to assess the stability of excavated rock slopes in the field as rock mass conditions become visible during construction is required. So rapid field assessment method is what is required, and this rapid field assessment method must be able to must help to provide long-term stable slopes by adjusting slope angles that helps to reduce maintenance and bench width needs due to local failures. So if you get a method that enables us to conduct rapid assessment of the excavated slope that is already excavated and the real condition is manifested, so the site engineer or engineering geologist on site can observe the excavated slope and apply this fastest technique, and if he can provide the optimum slope angle for the cutting of the slopes, then that method will be the best method. There are some methods. Rapid assessment of stability and optimal slope angles of cuttings can be carried out using stability charts like this. So stability charts like this can be are conventionally or commonly used to provide optimal slope angles in the cuttings during the excavation on site. However, these methods, stability charts, are also kinematic methods, approach of limit equilibrium methods, and they require some inputs like internal friction angle, unit weight, cohesion, and so forth. And also these charts are most effective when the geometry, geology, hydrogeology, geomechanical properties of the slope under review or under construction are similar to known performance of precedent slopes. This is a challenge for the site geologist, where the actual ground condition that is manifested by excavation is not quite equivalent or similar to the known performance of precedent slopes, then it will create a difficulty for decision making of the site engineer or engineering geologists. Therefore, there should be another method that is applicable by the site engineer or site engineering geologists who are responsible to conduct the rapid assessment and make optimal slope angles for the cutting of the excavation of the slope without the excavation being stopped. So that type of method is required, and there are different methods, especially there are several empirically derived methods developed in the last 50 years, and the following empirical methods are commonly used to derive safe slope, appropriate support, and reinforcement. And there are 6 empirically derived methods here listed here: Q system by Barton et al. 1974, rock mass rating Bianisky, slope mass rating Romana, modified rock mass rating Yunal, global slope performance index Sullivan, and Q slope method by Barton and Barr since 2015. These are among the methods that we will see in the next episode. We will see out among these methods which method is the best method and which can be utilized, applied by site engineers and field geologists or engineering geologists who can make judgments on the excavated slopes to provide a suitable safe slope angle, appropriate support, and reinforcement. Therefore, we'll discuss about the best method out of these empirically derived methods in the next episode. Therefore, stay tuned to the crucial insights we're gonna discuss in episode 2. Thank you.